Okay, we're going to wrap up the chapter in this video covering both parts 5 and 6. We will start in part 5 talking about how we use scientific research to determine nutritional needs. And I kind of mentioned this in the last part of the chapter from the last video, that it's really important when we give nutritional advice to make sure that that advice is evidence-based. I can't hit that home hard enough. Evidence-based nutritional and scientific recommendations, they need to be based in the literature, based on scientific study. So I kind of briefly on this slide want to introduce you to the scientific method. Again, if you've taken a biology course, or really probably any science course, you've probably heard about the scientific method. The scientific method is used by scientists to conduct research and to make sure that their research is, unbiased and appropriate. And so here we go. So the scientific method starts off with making observations and asking questions. And there's an example underneath here that's nutrition related, so I'll read it. It says, in the mid-1950s, physicians saw or noted that in short-term experiences, people eating a low-calorie, high-protein diet lost more weight quickly than people eating a low-calorie, high-carbohydrate diet. So there's some observations that were made there. They then generate a hypothesis. Scientists generate a hypothesis. Low-calorie, high-protein diets, like the Atkins and Zone diets, lead to more weight loss over time than low-calorie, high-carbohydrate diets. Research is done. Okay, so for a year, researchers followed people. As a side note, nutrition experiments using humans are very hard to do. Okay, so for a year, researchers followed people assigned to either the low-calorie, high-protein diet or a low-calorie, high-carbohydrate diet. At the end of the study, weight loss did not differ significantly between the two groups. Interesting. Okay, here's 4. Findings evaluated by other scientists and published. Okay, so this is a really key step in the scientific method, is this peer review step. Really, really important. So a peer review, this is going to be a review by other scientists in that field that really know that line of work. Okay, so other, nutrition scientists in this case. A peer review indicated that the study was conducted in an unbiased scientific manner and the results appeared valid. And so the study was then published in a very reputable journal called the New England Journal of Medicine. And there's the actual date of the publication. Step 5, other studies are conducted, right? So one study is not good enough for the entire scientific community to be like, oh, this is what we accept wholeheartedly. So follow-up studies and experiments were conducted to confirm and extend the findings. So here's another study done in 2005, looking at low-calorie, high-protein versus low-calorie, high-carbohydrate. And again, at the end of a year, the two groups did not significantly differ in their weight loss. They probably both lost weight. Low calorie, if you're in a calorie deficit, you're going to lose weight. In 2007, another study was done that was published in the Journal of American Medicine. In 2012, another study done, published in another, journal. This time with diabetics, right? Yeah, type 2 diabetes. Again, no difference. 2018, another study. Slightly different. This one is only 8 weeks. Again, confirmed on average that there was no difference. So, you got 4 more studies confirming what was found in that first one. And so at that point, the scientific community, might say there is enough scientific evidence here to draw a general conclusion and to either, in this case, accept or reject. They would accept the hypothesis. Okay, so again, based on current available research studies, the hypothesis is not accepted here. They're going to reject it. okay, because there's not a difference between the two. If over the next 10 years, many other studies come out and what we find is that this isn't true, then we may change our conclusion. And that is something that a lot of times the general public, who are not in the field of scientific research, it's hard to accept that things change in science. We may think one thing with evidence to support why we think it, for a couple of years, and then new studies may come out looking at things differently, and the outcome may be different. And so, that's tough for a lot of people. But that's the way science goes, right? We follow this scientific method. There is a really rigorous peer review process. There has to be a large body of evidence, for these general conclusions to be made and for recommendations to be made in the field of nutrition. Okay, so evidence-based, very, very important. Let's talk a little bit about how some of these studies are done. So a lot of times studies will begin in laboratory animals. So laboratory animals, they're used when scientists cannot ethically test their hypotheses on humans, or when scientists want to start their research, in animal models and then go to the human model. That can happen as well. There has to be an appropriate animal model in order to do these studies. There are various animal models that can be used. Depends on what we're looking at. Okay. Some diseases in lab animals closely mimic human diseases, and so those are perfect models. Here's an example. In the early 1900s, scientists showed that thiamine, which is a type of B vitamin, cures a disease in chickens that is just like a disease that humans can get when they have a deficiency, beerberry. So this was a beerberry-like disease in chickens, okay? In humans, the symptoms of this disease are things like fast heart rate, shortness of breath, swelling of the legs, numbness, confusion, trouble moving legs, and pain. Scientists used chickens to determine the cause of the disease, and we figured out it was a vitamin B deficiency. So this was a great model. Unfortunately, many human chronic diseases, there is not a laboratory animal model that we can use. They're just not mimicked. Okay, so animal models are great when they're available. Human experiments can also be done. Again, human experiments must be ethical. You can't take, a human population of, 100 people and say, we're just going to not give you vitamin B and we'll see what happens. It has to be ethical. Any human experiments and animal experiments actually have to be reviewed by a research review board. And this is going to assess the risks and benefits of the study. And again, this animal studies are not done willy-nilly. Animals still have to be ethically treated. Not the same exact rules apply that would apply to humans, but there is a process still for using animal models. With humans, there has to be informed consent. And so any participants in a study have to be informed of the study's purpose, the procedures, and the known benefits and risks. So there's more red tape to doing human studies. Okay, so here's one type of human study that can be done. This is called a case control study. So in a case control study, the individuals who have consented to this, right, they have a specific condition, so they are the case, and we compare those to individuals that do not have whatever this condition is, and we call those the controls. Okay, here's an example. It's not nutrition-based, but it's still a great example of a scientific study. So for example, we can compare those with lung cancer to those without lung cancer, right? So the people who have the lung cancer would be the case, and the people that do not have the lung cancer would be the control. So it's a case control study. The strongest studies compare groups that are similar in age, race, and gender, so that there aren't any other factors, any other variables coming into play. Some limitations of case control studies is, in the end, you can't claim cause and effect. You can show maybe a correlation, but you can't claim cause and effect. These are used more as a way to give researchers clues about diseases and less to say this is the cause of this. Even if you're controlling for age, race, and gender, in human studies, it's hard to control for everything. So another example of a limitation is that there could be differences in nutrition and physical activity, lifestyle differences between the two groups that are very difficult to control for. So these studies are good, but again, there are limits to these studies that we have to keep in mind. Okay, double-blind studies. Again, human studies. These have features built in that help to reduce bias. So in a double-blind study, neither the participant nor the researcher who's conducting the study knows which group who's in, okay? The expected results of the protocol are not disclosed, and that reduces what's called the placebo effect. Okay, so it may only be possible to do studies that are single blind, where the researcher knows, but the participants do not. But again, the best would be a double blind study where neither the researcher or the participant knows, which treatment they're getting. Okay. So human studies are a little bit more difficult to do than studies in animals, but they're a little bit maybe more meaningful because they're done in humans and we're concerned about things that are happening in humans. Okay, so I want to kind of hit this home one more time. We talked on, I think the first slide, about the scientific method, and we briefly talked about peer review. So this is a really important step in the process of the scientific method. And so prior to publishing results in a scientific journal, other scientists review studies. And they look to make sure that the study is unbiased and that the findings are objective. So here are some examples of reputable peer-reviewed journals. The American Journal of Clinical Nutrition, the New England Journal of Medicine, the Academy of Nutrition and Dietetics Journal. These are all journals that would publish nutrition-related studies. Okay, so let's say an experiment is done, the peer review process happens, scientific researcher, a nutrition PhD, publishes their findings in a reputable scientific journal. It doesn't end there. There are follow-up studies that will happen, right? So one experiment with, results that, support a hypothesis, let's say. One experiment is not enough to say, yes, that hypothesis is true, right? Instead, good science, there will be multiple experiments that are done, as follow-up experiments to confirm or disprove that the original experiment, had value, had weight to it. So we have to have multiple publications, multiple sources of evidence to support a hypothesis. That increases the level of confidence in specific findings. So on the next slide, I kind of show this. Okay. So again, one study is not going to be enough. So this is on type 2 diabetes, right? And the hypothesis is that obesity leads to type 2 diabetes. So there'll be observations that are made, right, by clinicians, by physicians that indicate type 2 diabetes is much more common in obese patients than in leaner patients. There will be some epidemiological studies that show type 2 diabetes is more commonly found in obese populations than leaner populations. So there we've got two sources of evidence, and then there'll be some studies done, right? So studies might start in laboratory animals where they show that overfeeding these animals leads to obesity, and then often leads to the development of type 2 diabetes. So there's really good evidence. There might be a case control study, in humans that shows that obese patients are much more likely to have type 2 diabetes than the leaner comparison group that is matched for all the other characteristics like age and race and gender. And then other human studies that show that weight loss maybe can correct type 2 diabetes in many people. Laboratory research also show that enlarged fat cells associated with obesity are much less responsive to normal hormonal signaling involving blood glucose. So this huge, body of evidence, multiple studies, would increase confidence in that research hypothesis that was originally stated, right? That obesity can lead to the development of type 2 diabetes. So again, it's not just one study. There has to be, a wealth of evidence to support in order for, kind of claims to be made. Okay, so there's got to be this critical evaluation and synthesis of all the research. That's what evidence-based science is. Okay, and this last part of the chapter, I like this part of the chapter, how to evaluate nutrition claims, products, and advice. Okay, and so you want to always apply the basic principles of nutrition. You want to be cautious if, on a label or from an influencer, if only advantages are discussed, right? If you're only being told the positives and none of the side effects or the negatives, you want to be careful. You want to be careful of new secret breakthroughs, claims to cure a disease. If it sounds too good to be true, it's probably too good to be true. Extreme bias against the medical community. Don't trust your doctor. Trust me. Be very cautious. Testimonials that show dramatic results. Be cautious. Okay, so lots of people trying to make money off of nutrition-related things. The person who is trying to get you to buy into this, either monetarily or trying to get you to do this thing, do this exercise or eat this food or avoid these 5 foods or take this supplement. What are their credentials? And if it says doctor so-and-so, figure out what kind of doctor. What does that mean? Are they a PhD in nutrition? Are they an MD? Are they an RD? Do they have the proper credentials to be giving you, nutritional or any advice that's based in science? What is the research behind these claims? Is it good research? Look at the study. Nutrition studies are hard to read, but there are PhDs that are on social media that are breaking down research and showing you this is a good study, this is not a good study. They're very interesting to watch. What is the size of the study? Were there enough participants, or was this done in like 5 people? Okay. What was the duration of the study? Was it a year long or 10 years long, or was it 2 weeks? Okay. The type of study, be very careful, be discriminating. Marketing companies don't always have your best interest at heart. Influencers are trying to sell you something. So just be very cautious. Okay, buy nutrition-related products. The Dietary Supplement Health and Education Act, DSHEA for short, that was passed in 1994, and this act classifies vitamins, minerals, amino acids, and herbal remedies as foods and not drugs. Okay. This restricted the FDA, the U.S. Food and Drug Administration, from rigorous regulation. They still regulate these markets, but it's a little different. So the FDA has to prove that these products are unsafe to prevent sale. Okay, rather than the company that's producing these products proving that they are safe. It's kind of the opposite, the opposite way around here. Okay, so how about when a supplement, herbal supplement or vitamin, how about when there's claims on the label, right? And so here's an example here. This is ginseng extract, and if we look down here, there's the nutrition facts panel, and then there's the ingredients list. It tells you, where it was made and distributed, suggested use, and then there's a claim. It says, when you need to perform your best, take ginseng, okay? If there is a claim on the label, so this is saying you're going to perform your best if you take this supplement, the FDA requires there to be this statement. It says this statement has not been evaluated by the Food and Drug Administration. This product is not intended to diagnose, treat, cure, or prevent disease. Okay? So, again, unlike how the FDA regulates drugs, it's a very different process. And so because of that, because these are categorized as food, if there are claims made, there has to be this statement on the label. Okay, so that is it for chapter 1.